Welcome back. Today, in this video, we're going to focus on a very, very important law in electrical circuits. I would say after Ohm's law, this is critical law. It's called the Kirchhoffs law. It's a very universal law. We're going to introduce it only for resistors and power sources, but it would work with much more complex circuit with much more diverse components. But our goal is to learn kind of how to apply it and the basic steps in the process. Kirchhoff's law has two powerful variations. One is called Kirchhoffs Current Law. The other one is called Kirchhoffs Voltage Law. For the work we're going to do in this video, we're going to strictly focus on the Kirchhoffs Current Law. And we're going to leave the Kirchhoffs voltage law for a later date. It's just a variation on current law. But they both can solve problems equally well. In some cases, Kirchhoffs voltage law may be easier. In some cases, Kirchhoffs current law may be easier. But they're both very, very powerful tools and allow us to analyze circuits of any size. Most of the stuff we do by hand is going to be circuits that have maybe 10, 20 components on them, the max, but you could work on components like a microprocessor, which has millions and millions of circuits in there, and is able to apply exactly what we are doing here to analyze. And of course, we would use computer systems to help us do that. But the process, the steps you go through to analyze the circuit would be exactly what we're discussing here. So now that so we know that this is probably the second most important law after Ohm's law. Now let's go to jump right in and say, okay, exactly what does it do? How does it work? What are the steps in the process? So let's go there next. So oops. Didn't mean to move that one, move the page. So Kirchhoff's current law basically has 4 steps. And once we get good at it, we can more or less get rid of step 2 altogether. But for now, let's kind of have it in our 4 steps, step 1, step 2, step 3. And let's kind of walk through it for this circuit. This is kind of a nice circuit for us to walk through it, okay? So step 1 and 2 is kind of done for us because I didn't want to take the video time drawing these things. So let's walk through it and see what it says. Step 1 says when somebody gives you a circuit and say, analyze this circuit, you draw it on a plane, on a piece of paper, flat. It's got to be flat for this thing to work. And then you say, okay, if that is the case, and when I've done that, here's the circuit. First thing I need to do is identify all the essential nodes. So what is an essential node? Essential node is when 3 or more than 2, depending on how you want to say it, when there are at least 3 elements come together. It could be 4, 5, 6, but at least 3 have to come together for it to be an essential node. If only 2 come together, it's a node, but it's not an essential node and we don't care about it. For KCL to care about a node, it has to have 3 elements coming together. 3 resistors, 2 resistors and a source, 2 sources, whatever the case. It's a combination, doesn't matter. You just got to have 3 or more things come together. So in our case, if you look at this circuit, you will see that we have how many essential nodes. I'm going to use the red. So we are on step 1 and we're trying to identify essential nodes. So here is one. There's this R3, R1, and R2 coming together. That's 3 items, 3 components, therefore is an essential node. And then right here is the second node. We got R3, R4, and R5 coming together at a point. So that's the second essential node. And the last one is where R5, R4, R2, and current source I1 is coming together. So remember, just because it's a point or a line, it doesn't matter because We are an ideal circuit. That's just one node because the voltage across this whole piece of wire is exactly the same. Okay, so that's step one. Step one is to figure out how many nodes I have. So now we know that the number of essential nodes I have in here is equal to 3. Okay, one of those essential nodes, and you can literally pick any one you want. One of those nodes, you can just arbitrarily call it V reference and sets its value to 0. You can pick any, it won't make any difference which one of the nodes you pick. Just pick one and call it that, which then means that if I have 3 essential nodes, one is going to be referenced. I only going to write equation or worry about 3 minus 1, one less than the number of essentials. So that's how many equations I'll end up with when I've worked on this one. Okay. So does that make sense? Then once we figured out what the essential nodes are, we picked one to be a reference. The next step we need to do, we need to go through this thing and label all the currents leaving the node. Notice I go to V1 and I draw I1, I2, and I3, all leaving the node, meaning they're pointing out from the node. For us, we're going to always do the same thing, but there's nothing in nature which says that that's what you do. The reason we do it is that consistency helps us be more predictable and don't have to think too much about it. We just draw it always going out, no exception, absolutely no exception. And so we go to the other node, which is V2, and we draw all of these out, okay? So now we have 2 equations. So now we are in step 2, right? We're in step 2. Let me change color so we know which step we are in. We are in step 2. We drew all the I1, I2, I3, I4, I5. And now what we're going to do, we're going to get to step 3, and I'm going to use green for step 3. Now we are in step 3. And in step 3, what we're going to do is we are going to go ahead and write an equation. We're going to write, this is the way we do it. If we are in step 3, so we're going to do a KCL equation at one of the nodes, and then we come back and do a KCL equation at the second node. Now, what KCL tells them, the rule says the sum of currents leaving a node must add up to 0. All the current leaving a node must add up to 0. Another way to think about it, everything that comes in must go out. Everything that comes in is negative. Everything that goes out is positive. If you add them all together, it will be 0. Think about a hose connected to something. Whatever water comes in must go out. It can't. There's no place to store it, right? So that's the same concept here. So if you're here, then how many currents are leaving the node? We have I1 leaving, right? We have I2 leaving, and we have I3 leaving, okay? That's equal to 0. Step 3 is and then we go to the second one. It says, okay, I4 on that node, I5 and I6 are the 3 things there that are leaving, and they must be 0 as well. Okay, so that's all you do in step 3. Okay, since I had 3 essential nodes, one of them was a reference, and I do not write an equation for that. So I only had to write 2 equations. So it's always, if you have n nodes, then it's going to be n minus 1 equation. This is an important concept to remember. So far, so we got our KCL done. That's all KCL says. Boom, done. Now what we're going to do, we're going to go to step 4, and I'm running out of color. I thought I had black. Maybe I don't have. Well, let's see if I. Yeah, let's go ahead and get a black. Okay. So if I have so we're going to do step 4 in black, and step 4 basically says what my goal is. In the end, right now I've got 1 variable, 2 variable, 3, 4, 5, 6 variable and 2 equations. My goal is to end up with only 2 equations And the only unknown in those equations would be V1 and V2. That's my goal. The only unknown should be the voltage for V1 and V2. By the way, remember what we said, V1 basically what it's indicating that the voltage V1 is from here to here. It's the difference between there to the reference. V2 is from here to here, which is there to the reference. So I want to make sure those are all clear as we go through it. Okay, so what do I do next? The next is I have to use Ohm's law, or whatever I know, which is basically Ohm's law, to write all these currents in terms of V1 and V2, unless somebody gives it to me, okay? So let's go ahead and go through this and see if we can write I1, I2, I3, I4, I5, and I6 in terms of V1 and V2, okay? So in order to do that, I need a little bit more room. So I'm going to go kind of on the side here. So we are in the last step. We are almost home free. We are in the last step. We are trying to do that. So let's take a look at I1 and see if we can do I1. So I1 is equal to whatever current is in here. Hey, they're telling me that is 2 amps, but the 2 amps is coming this way, which we know in a given branch, the current is the same regardless of where I'm looking. So in this particular case, then they've already given me the current is 2 amp, except it's going in the wrong direction. So all I have to go is coming in, which is negative direction. Everything leaving is positive direction. So I'm going to call it -2. So I1 is -2. I am done. Now, I2 is a little more tricky. I2, I have to do a little bit of Ohm's law play, which says from here to here, the voltage is V1. Remember, that's the definition. When you say voltage is V1, it's from here to the reference. So here it says it's V1. So I can use V over R to find the I. So it's going to be basically V1 minus 0 divided by 10,000. And that gives me I1, okay? Now, what is I2? I'm sorry, I2 I already have. I3 basically is the current that flows in this direction. So if it's flowing in this direction, I can take this voltage, subtract that voltage, because it's not, this is from here to here, this is from here to here. But if I subtract V2 from V1, I find the difference between those two. So it'll be V1 minus V2 divided by 40,000. And notice I'm translating everything to ohms, so there's no funny business about current is in what unit current is in, what unit voltage is in. We know voltage is going to be in volt, current is going to be in amps. Okay. So now what we've done, we found I1, I2, and I3. All we need to do is find basically I4, I5, and I6 for the second equation. And we just do the same thing. Now, look what happens to I4. I4 is actually assumed to be going the opposite direction. So now we have to take V2 minus V1 divided by 40,000. Okay, I5 is going to be from here to current that flows in this direction. So what we can do is we can say, okay, that is V2 minus 0, the voltage from here to here, divided by 5,000, which is the resistance. See what we are doing? We're applying Ohm's law. And then for the 8K is going to be voltages again from here to here is V2 minus 0 divided by 8,000. Okay, so now what I can do, now that I have that information, I can take it and write all the I1 in it. So I can say it's -2 plus V1, and I'm going to drop the 0. Don't need to write the 0. 10,000 plus I3, which is V1 minus V2 over 40,000, sorry, 40,000 equals to 0, because that's what Kirchhoff's law says I should do. And then what I could do, I can go ahead and take the I4, I5, and I6 and do the same thing. So, so I can do V2 minus V1 over 40,000, okay, plus V2 over 5,000 plus V2 over 8,000 equal to 0. Now, the beauty is now I have two equations, two unknown, and I can solve it. Now, if you do it manually, you basically find a common denominator. The common denominator for this is 40,000. So you multiply both sides of the equation with 40,000, and this gets simplified to minus 80,000 plus 4V1 plus V1 minus V2 equal to 0. This one, the common denominator is once again 40,000. So it will be V2 minus V1 plus 8 times 5,000, right? 40,000 was the common denominator. We multiplied to both sides with 40,000. So we'll have 8 V2 plus 5 V2 equal to 0. So all we have to do now, basically we are going through algebra, something you hopefully have had algebra. If not, then now is a good time to practice it. And then what we're going to do is continue on. I'll get myself a little more space. Basically what we're doing, we're taking this equation and keep simplifying it. So until we can solve it. So when you kind of clean this up, you'll end up with 5V1 minus V2 equal to 80,000. And then this bottom one is going to be minus V1 plus 8 and 5, that's 13, plus 1 is 14, 14 V2, so equal to 0. So we can do this by substitution, meaning that on the bottom one, we can find, for example, V1 is equal to 14 V2. We can take that, substitute it up here. And substitute it in here. And what would actually, let's not run into something else. So I can substitute it in the top one. So 14 V2 gets substituted for 1, 5 times 14 is going to be 50, 70. So what we got it. So that's the top equation. The top equation is going to be basically 70 V2 minus V2 equal to 80,000. And once we solve this, we get V2 equal to 80,000 divided by 69. And then we can take this, plug it in here and get V1, okay? And V1 is going to be 14 times 80,000 divided by 69. So we got a V1. Great. So we're pretty much done. Whatever you want to find, we can find. I have the voltage up here. I have the voltage up here. I can solve it and find everything that I need, okay? Now, if you're comfortable, one thing you want to notice, if you don't want to write this step, I would encourage you to continue to write it until you're comfortable. But if you don't want to write this equation, you can kind of mentally do this. You say, okay, I'm going to this branch, find the current is -2. Here, I know the current is going to be the voltage divided by 10 by the resistor. I know here is going to be this voltage minus that voltage divided by 40,000. Here, I know it's going to be this voltage minus that voltage divided by 40,000, this voltage divided by 5,000, and this voltage divided by 8,000. So if you want, again, once again, you really got to be doing a bunch of these problems before you can skip this step, but you can skip drawing I1, I2, I3, because that was an intermediate step to show you how you can do that, okay? So you can directly go in here. I highly recommend that, much like what I did in here, you be very clear you're doing KCL and which node you're writing. So you can follow it, and whoever is reading your solution can also follow it. Okay, and these are not equal sign, these are arrows, right? Going from one to the other. Here are the steps, here's how you do it. So let's do that. I have another circuit here, which I wanted to show you how. I'm gonna just go ahead and grab this piece if I can, and let's see if I can. Oops. Put another circuit in here. I think this is like one of the last problems, problem 15 in the homework that you have to work on. I'll put it up here. So one of the things you want, let's go through the exercise. What's the first step? The first step in the process is to identify nodes. You might want to put this video on pause and try to see if you can figure out what are this, how many essential nodes you have, and then come back. I'm just about ready to go through and identify them. So you might want to do it yourself just to see if you can figure out what the step one, all the essential nodes are. As far as I can see, this is one essential node. This is another one. This is another one. Okay. And this is another one. Okay. So I have four nodes. One of them, and usually I pick the one that has the highest number of branches. This one has 1, 2, 3, 4, 5 elements coming to it. So I'm going to make that the reference. And I'm going to say that is equal to 0. Remember, I can do that. And then I'll name the rest of them simply V1, V2, and V3. And this time I'm not going to go through. We know that we're going to assume all the currents are leaving the node. That's the positive direction for the way we write the equations, right? So what I'm going to do, just as we are here, we finished step one. Step two, I'm going to kind of say, okay, we know well enough. We're going to kind of skip it because we know what we are doing. We are summing all the currents, and I'm going to jump right into writing the equations. I know I have to write let me use a black pen. So I know I have to do a KCL at node V1, write an equation for that. I got to write an equation at V2, and I got to write an equation at V3. Okay. So how do I do it? Well, I'll start here, but say, okay, what is the current going this way? Oh, they've already told me it's 25 milliamp. Remember, I'm going to turn everything into amps and volts and ohms. So I don't have to worry about conversion of units and that kind of confusion. So we're going to say, okay, the V1, I've got current going down this branch with a 25 milliamp, but the current is coming in. So it's a negative opposite direction. So it's 25 divided by 1,000. That's an amp. And then I'm going to say, okay, there's a current going down to 10K I have to worry about. That is going to be V1 minus 0. If you want to write it, that's great. Divided by 10,000 because that's the ohm. And then V1 minus V2, the voltage here, divided by 15,000. Okay. So that's voltage for one. And then V2, now I'm going to go to node V2 and take a look at that one. That gets a little bit more interesting, and I want you to pay attention to, because the goal for this whole circuit is for us to find V1, V2, and V3, but you already know this voltage is 0. You know this is stepping up. The voltage difference from here to here is 5 volts. So if this is 0 and this voltage is stepping up 5, so what is the voltage here? Voltage here is already given to me, is equal to 5 volts. I don't even have to write an equation. V2 is a poof right there for me. Okay, And then we're going to go to V3. V3 introduces a few other interesting things we got to pay attention to. One thing is so it says, okay, let's take a look at what's going on. So there is a branch here. So the current I want going out, but there's a 20 milliamp coming in. So I'm going to write it as minus because it's coming in. It's going to be minus 20 divided by 1,000 plus. And then here, I'm going to look at this and say, okay, here is 0. This is plus, so it's higher, 4 volt higher. So this place must be 4 volts. So now if I want to find the current here, it's going to be V3 minus 4, not 0, because you got this thing here, V3 minus 4 divided by 5,000. Ooh, and I got a couple other ones to worry about. I got to worry about this one, and I got to worry about this one. So let's do the 10K first. That is going to be basically V3 minus V2. That's the voltage difference from here to here. And it's divided by 10,000. Plus here, from the 5K, it's going to be V3 minus 0, because this is 0 divided by 5,000 equal to 0. Now I have 3 equations. Solve it. You can find the V2, substitute it there, take a common denominator, multiply both sides, and solve to find V1, V2, V3. Remember, when you do KCL, your job is to find V1, V2, V3. And if somebody gives you the voltage automatically, don't fight it, take it and run with it. Now you could do this by hand. And I want to introduce you to your calculator is also capable of solving equations. And there is another tool available online free. It's called Wolfram Alpha. It's a website. And I'm going to bring it up so you have seen it. This video is going to be a little longer than our normal video, but I think it's for a good cause. So let's go ahead and bring up Wolfram Alpha. So that's a tool that makes it a little bit easier for you to solve some of these things without having to do it by hand. So here is the website. I just kind of grabbed it. It's called Wolfram Alpha. And all I have to do is I basically enter the equation and it solves. The only problem it has, it doesn't like you naming variables V1 and V2. So what I'm going to do, I'm going to call my V1A, V2B, and V3C. So that's how I'm going to get around the problem I have with Wolfram not liking variables named V1, V2, V3. So what I'll do is I'll just basically say minus 25 over 1,000. See what I'm doing? I'm just basically writing the equations I have. V1, remember, we called it A over 10,000 plus A minus B over 15,000 equal to 0. And all I do is put a comma in there and do the second equation. The second equation is pretty simple. B is equal to 5. And that's it. And then the last equation I have, the third equation I have is minus 20 over 1,000 plus V3. Remember what we called V3? V3 was C. So it's going to be C minus 4 divided by 5,000. It would be good if I got the parentheses in the right direction. There we go. And then we have V3 minus V2, which we're going to call C minus B over 10,000 plus C over 5,000, and all that equal to 0. Okay, so I've written all the equation. One feature I really like about this is when you write it like a flat, using flat notation like I have in here, that's the only way you can type it in on your normal keyboard. It's hard to know if you typed it correctly. What I really like is after you hit enter, it writes it in the way humans like to write it. See how it puts it in minus 25 over 1,000, A over 10,000, A minus B over 50. That looks good. B equal to 5. That looks good. Minus 20 over 10,000, C over minus 4 over 5,000, C minus B over 10,000, and C. Perfect. Perfect. So those are the equation. he solved it and gave me all the answers, and usually likes to give it to you in a fraction, especially if the numbers do not end up being a clean, rational number. If you can, they go on forever if in a fraction form. But you can, I think you can ask him to give you this stuff. Oh, you can ask him to give you the numbers in a decimal form. Let's see. Oh yeah, decimal form. I kind of like the numbers in decimal form. So what he's basically telling us is that when you solve this equation, V1, oops, it went away, so I'm going to write it. So, oops, that's not it. So it basically gave us V1 is equal to 152. V2, we already knew what it was. And V3 equal to 42.6 volts. It's really important to write the units next to your answers as well. And it's also a good habit to somehow put a box around final answers so anybody who's reading it know where they can find the final answers. Like me trying to grade your homework or exam, it would be very helpful to have that. So those are good habits to pick up. Okay, so this was an example of doing Kirchhoff's current law. That's the one we're going to focus on for this course. So let's go back and review the steps one more time just to make sure we've got the steps all correct. Okay. Let's see if I can find some open space for us to look at this thing. Okay. So first step in the process is to identify essential node. Essential node is where 3 and more elements come together. Okay. You can either physically draw the current or mentally remember that there is current leaving the nodes. You have to sum all the currents leaving the node. And then step 3, you write the KCL equation. So in most cases, once you get comfortable, step 2, 3, and 4, you may combine them all together and do it in one pass, as I did on the second problem. But if you're not comfortable, I would encourage you to do it step by step as it's outlined here until you become comfortable and do it. Thanks again for watching. That brings us to the end of the video on KCL, Kirchhoff's Current Law. It's probably one of the most important laws right after Ohm's law. Have a good day.